And again, a very good day to everybody. I'm going to sort of change this sort of take a bit today, this afternoon. This morning, we'll talk about something that's pretty fluid, with no dimension, with no sort of limitations that changes all the time. In this case, I'm going to talk about catchment geochemistry. And I'm sort of leaning it towards the new economic minerals exploration. And I think this is something we heard a lot about it yesterday. We talked pretty much seriously into the sort of mechanics of the formation of new economic minerals, or critical minerals is what's been referred to yesterday. Today I'm going to go more sort of back to the basics in terms of exploring for the new economic minerals. Okay, in this talk, I'm going to talk about the state of play of these new economic minerals, or NEMI, exploration in Queensland itself. I'm going to stress really heavily on the importance of chemistry, and I'll show you why. I think, it's really fundamental. And by looking at the chemistry, we know how advanced is this exploration program itself. The talk, or the work for this new future exploration has to leverage really heavily on the work that's been completed in Queensland. And there are 3 packages of work that's been done. One of them is the National Geochemical Survey of Australia, which is a joint or collaborated sort of effort between the states and the federal government. The second one is a Cape York Regional Prospectivity Assessment, in which, from the output of the first package of work, we found that it's really very attractive, in the North Queensland area. And so we did a follow-up program of them. And finally, I'll touch very briefly on a Geoscience Australia initiative. That's the North Australia Geochemical Survey, which was completed almost at the same time as the Cape York work itself. And finally, I'll sort of put the challenge out, what's the exploration and targeting strategies? Basically, I think, the 3 amigos, Deputy, me, and, Dominic, which been in all this, work, are quite confident, especially in the Northeast Queensland, to tell you where to start looking, what to look for, and so that's something that, I think, we'll touch on later on. What's new economic mineral? Well, new economic minerals, or NEMI. It defines a group of technological or strategic or economical, group of elements that changes from time to time. At the moment, there are 42 elements that's in the current definition, and this NEMI that I use is linked to the CEI, or Collaborative Exploration Initiative, that the department has released, for this funding of, initiative. And so I've used the same 42 elements in this talk. Of the 42 elements, 9 of them are common metals, or base metals, or precious metal that has never ceased in its exploration. And so it's pretty well understood. However, there are 32 other elements, which I use the word less attractive or unattractive NEMI, that's really underexplored, or that's very little knowledge, or it's special distribution within the whole of Queensland. Again, I repeat that phrase that geochemistry is pivotal to this NEMI exploration itself. This periodic table shows all the elements that could be commercially analyzed in Australia. That's about, that's 71 elements there. Well, when you talk about chemistry relates to mineral, and mineral is the solid state representation of chemistry. The two are always interlinked. So when you look at the 71 elements, you can sort of catalog them into how it occurs in nature. Basically, we break it down into 3 groups. The rock-forming minerals, that's to say these are elements that forms the fundamental of rocks. The minerals forms the rock itself, and they are shown in the beige color. The other group in blue, it's the ore-forming minerals. These are generally very low concentration, and it has to be concentrated to such an extent that it becomes ore or valuable interest. The one in green are in between the two. It depends really heavily on how high the concentration is before it becomes an ore or becomes interesting to explorers. Next, we just superimpose a NEMI sort of group of elements. you find the first thing is said, the NAMI mineral falls into all these three groups. In other words, it has a very diverse origin. And so if you look at exploration, you have to use multiple exploration models to look for them. It's not just a simple one, sort of method to fit all. Precious and base metal never cease in importance, and so it's always been explored. Whereas most other NAMI minerals are not eye-catching. What it means is this: it's hard to identify. Say, if I give you, a piece of one of these NAMI minerals, I'll show some example later on. It's not eye-catching. It doesn't attract you. It hasn't got a flashy sulfide goldy look, to be interested in. This is a typical example, for example, of some of the NAMI ore bodies itself. Lithium generally forms in salt lakes, or in clays, or in mica that's formed around alteration halos or metasomatic halos, or in metamorphic halos. And the traditional sort of thoughts that we had for lithium is that, oh, it's nice pink color lepidolite, or a spodumene and all this, But in general, the majority of them are just dull, chalky looking white stuff on the ground. And I bet all geologists like us, we probably stumble across it and swear at it and do not know the worth of that, pile of dirt. That's typical because it's not attractive enough for us to know that's lepidolite. Similarly with magnesite. Magnesite, if you're thinking of magnesite, it's a typical, sort of cauliflower type, good luck. Because all the magnesite deposits that I know are sort of multivariate colors, from white to gray, to brown color, and forms chalky bands, within sediments. And unless you analyze it, you will know it's magnesium there. The other sort of group which is common is the detrital ones. It goes from mineral sands to gravel. A good example is detrital or heavy minerals. Most heavy minerals just form streaks on the beach or in sand, or it's a layer in sedimentary rocks, in sediments or sedimentary rocks. Basically, when you look at detrital sort of sediments, you put in your hands, you don't know what it contains, whether it's just iron oxide, or it's rutile, or it's zircons, or it's rare earth, because it could contain a lot of rare earth as well. Unless you analyze it chemically, you wouldn't know. It's just, magnetite is easy. You put a magnet, you sort of suck it up, but what else is in the magnetite? So you have to use chemical to differentiate it. The coarser minerals, you can identify it, like, the coal tar, which is tantalum niobium or tin. People could pan it, and if it's coarse enough, they could identify it's ore, or it's just, black stuff. So in other words, you really need chemistry to explore for NAMI minerals. Probably in Australia, one of the common sort of ore material that we are all familiar, we can tell what it is, it's bauxite and silica sand. We can tell it's bauxite, silica sand, but is it worth to be called an ore, or is it just dirt on the ground? And that you could only tell when you analyze it to see whether the grade is good enough or it's pure enough to be, sort of bauxite or high purity silica. We talk a lot about rare earth. This is a picture I think, Matthew sort of showed yesterday. I bet you, if I put a pile of this dirt on, the doorway, everyone would just walk around and just, not knowing what it is, because it doesn't tell you what it contains until you analyze it. Otherwise, it's just a pile of dirt. And that's the problem with a lot of this rare earth. It's not eye-catching enough that you could readily go out and pick it up. It depends on a lot of analytical technology. And 20 years ago, it's very difficult to analyze for rare earth, tin, tungsten, etc. And so it's one of those elements that's in the back sort of, burner all the time. This reflects really well in terms of exploration as well. Okay. This is a snapshot of some of this geochemical exploration data. Here I pull out some of these stream sediments. Most NAMIs are underexplored. There are a certain group of NAMI minerals, and the 9 of them, copper, lead, zinc, gold, silver, cobalt, tin, tungsten and moly, and nickel. These 9 elements makes up about 85% of the data in our database, or in most exploration database. That's because these are important, and they never sort of lost favor in terms of exploration. The other sort of 6 elements, magnesium, aluminum, titanium, vanadium, cadmium, and tellurium, these are generally associated with either bauxite, silica sands, or the mafic minerals that people explore for, or associated with other ore deposits. And so there is about 10% or less than 10% of this data in there, but a lot of them are targeted to very specific ore deposits. The other 26% makes up of less than 5% of the geochemistry. We talk about less than 5%, and there is a lot of overlap, because if you test for one rare earth, you probably test for the other 9 as well, or other sort of 15 as well. And so there is an overrepresentation in data, but in real fact, it's really underexplored. This reflects very closely with the sort of discovery of minerals in Queensland itself. The diagrams that you see here, it's an example of gold occurrences in Queensland. You find that majority of them, firstly, occurs in the exposed part of Queensland, and secondly, it's really well sort of discovered in most part of Queensland itself. Similar story for copper zinc. I dropped lead is because lead doesn't make to the NAMI list in the current NAMI list. Also for tin, tungsten, and moly, and also nickel and cobalt. If you look at the actual number, there's about 21,000 mineral occurrences for silver, gold, copper, zinc, tin, tungsten, and moly. There are 189 copper nickel occurrences. The reason it's less is because we get less conducive geology for that sort of discovery, but there are lots of undiscovered ones that's yet to be found. Basically, the discovery reflects very strongly on exploration. And the lesser you explore, the lesser sort of deposits you find. For the other sort of the rest of the NAMI minerals, this is for the 6 elements: the magnesium, the aluminum, mostly the bauxites, silica sands, etc. It's really scattered throughout its sort of interest area. Similarly, if you look at platinum, palladium, it's scattered, very few, or group the other 26. There are only about 222 occurrences for the 32 NAMI elements. In other words, it's really underexplored and underrepresented in a big state like Queensland. What I've done here is to plot this different geochemistry in the sort of geochemical sort of stages of exploration. Basically, what we could say is gold, copper, silver, and zinc falls within the sort of more mature exploration stage. That's between, probably just past reconnaissance into the sort of prospect scale to the development scale. Tin, tungsten, and moly probably is around the prospect scale. Nickel, cobalt, aluminum, magnesium, it's between the reconnaissance to the prospect scale. Whereas the other 31 elements, we just begin the geochemical odyssey itself. It's basically underexplored. We don't know enough about it. Looks like a really sad story. Where do I begin? Thank goodness. The government, federal and state, has initiatives that help us along this way. I'll start with the first package, the National Geochemical Survey of Australia. It's a collaborative effort between states and government, and the federal government funded this program to look at every catchment within Australia. And so we sort of piggyback on this with, the three amigos covered every sort of catchment in Queensland. And so we produced the data and the samples for Geoscience Australia. The data is presented in the reports, which is released through Geoscience Australia as dot points or single sort of point data. What we've done in Queensland is we take the same package of data, but turn it into catchment chemistry. So basically it gives you a dimension where this chemistry or where this anomaly is. And so we have released this report, and I've given the link below as well as the link at the end of this talk, where you could go back. Basically what this report does is although it's a big scale, mega sort of, catchment, it will tell you where to look for certain elements that you are interested in and which area to look for. And that's the sort of power of this publication. Although it's very cost, it's a good start. The good thing about this national initiative is that it used a consistent methodology. What we've done is we took two depth layers, one from 0 to 20 centimeter, the other one from 60 to 90 centimeter. And these samples are taken at two size fractions, the 2 millimeters and the -75 microns. And all of these samples are sent to be analyzed using the same methodology. Every site has 21 subsamples and is analyzed using 6 methods. So in other words, it generates a lot of data. Sorry, okay. This is an example of the output that we've produced. Basically, it covers 69 elements. All the naming sort of elements that we talk about is covered by this program. And what you see there on your left is an example of one of the product, a page of the report itself, where it shows a gallium deposit. I think we did it slightly differently. We actually split it into 4 different maps in the atlas itself. That reflects different size and different depths itself. But for this presentation, I'll combine it into one single map. In this map, it shows you where the gallium anomaly is, which catchment to look for, and so it's really informative. It's a good start. Another one is for tungsten, where it shows a huge bands of anomaly up in the Cape York area. I don't know whether it's good or bad, but it shows you where to look for, and because of that, the government get really excited about it and gave us more money. And so we had another $400,000 to do this Cape York prospectivity studies, in which the 3 amigos back again. And we did a really comprehensive study of all these sub-catchments. At the same time, Geoscience Australia did a parallel sort of effort, as part of this North Australia Geochemical Survey. They look mainly in Northern Territory and cover part of this northern part of Mount Isa itself. And again, typical of Geoscience Australia is always point data. I'll talk about this briefly at the end of this talk. But for the North Queensland, we went through a lot of pre-preparations. What we've done is we look at the huge river basins itself. And within each river basins, you had catchments. And we split the catchment down. We look at the catchment, it sort of gets break down to sub-catchment and then down to what we call a catchment cells. It's impossible. It's really difficult to see at what level do we sample. So what we did is this is the complexity of all of them put together. What we did is we went back and looked at air photos, Google Maps, and DEM modeling, and try and merge together ones that we could see a good boundary in between. And what we do, once we have a sort of catchment, sub-catchment, we choose the lowest point based on DEM to take a sample at the lowest point. We are hoping that, because we are taking overbank deposits, really sort of churn up, mix up, that fine overbank deposits would represent the average composition of the catchment. Results is, as a result of that, there are lots of data. As I mentioned, one sample produces 21 subsamples, and they are analyzed, using 6 methods. So there are lots of data, just seas of data. The way we did this is that we appraised it at different levels, looking at different data types, different size fractions, different elements, different provinces within Cape York, different plots to compare them, and then normalize them and combine it together into one single map. And the method that we use is by weighting methods. So we do not omit any sort of size fractions or different methods, but using a weighting method which we think is effective to put it together into one map. This is an example of, the map that we produce. It's called Cape York Regional Prospectivity Atlas. It's both knowledge-based, it has database as well, and it identifies catchment. Besides that, we also create elemental association for that catchment, that particular catchment, which we also throw a possible mineralization model on top of that. Whether you like the mineralization model or not, it doesn't matter. But the association would not change. That mineral association is scientific and it would not change. This is the example of the tungsten that you look at. Very coarse, very happy for explorer. It's all over Cape York. But when we did the follow-up, probably a bit broken-hearted, it sort of shrink down to little catchment. Although it's small, it's very definite because I knew companies that went out, just because of this product being released, packed grounds on that area because they knew this is almost like a prospect scale, map to tell you where to look for. And I would not dismiss anything in the yellow or green because there are probably prospective as well. Similarly, if you look at gold, this is a gold map from the sort of cost national, NGSA sort of a map itself. Whereas the product that we carry, the sort of work that we carried out from the Cape York works gets narrowed down to very specific catchment that you could really go out, explore that catchment and find where exactly this, source of the gold is. Similar for bismuth, it's been refined down to sort of more sort of a bullseye, I use the word bullseye, to a sort of target zones that you could go out and explore. And for rare earth, this is neodymium that I'm looking at. It's all over the place, but when you narrow it down, it's very specific. It's a very specific catchment itself. I also combine all the rare earth as total rare earth, and that's total rare earth, has quite a big spread based on the NGSA. But based on what we produce, it has been narrowed down to very specific catchment. And for those who are exploring for NEMI, that's a perfect start. Well, because of the enormous amount of data, we try to do the lazy way, use principal component, throw it over and then get classes out. But after going through this data, the ergon value doesn't tell you very much at all. And so we sort of, this principal component is used just to confirm the association that we find. So what we did is that instead of using PCA, we went back to correlation coefficient, covariance, etc., and we go catchment by catchment to look at the elemental association itself. What we've come up is as such. This is one of the, I think, outcome of the report is we had different, the numbers are here, it's the field numbers, refers to catchment, what the cause is, and then we had this mineral association, or what's potential, and the mineral association and the models that we throw on top. And the models could be simplified into this map that you see here, where we had really rough sort of model, what's kind of mineralization to expect for those different catchment. We also had resource area for these different elements like silica sand, bauxite, etc. And you could read that report because it has been released already. So in other words, what we produce not only kickstart, but it really accelerate the sort of NEMI exploration in Queensland itself. The other product that I'm talking about is the North Australian Geochemical Survey, and it's a work by Geoscience Australia. And again, it's very similar concept. Their sample is slightly different because they do not take the 4 samples or the top and the bottom, but they take only one size fraction at the bottom. It's at like the 20 centimeter depth itself. And they do, the normal analytical thing and the MMI. So we would not integrate it into our sort of atlas because it just represents a portion of what we've used to create our atlas itself. That's for zinc and that's for cobalt. Now, where do we start? Well, that's a good question. Having this wealth of data from national to state, what I've done is I normalize, I look at 2 particular areas that's of great potential for NEMI expression. That's Cape York and that's Mount Isa. What I've done is I get the national average and normalize the data from Cape York and Mount Isa against the national average. The red, or the ones that's above that unity line, shows that these are enriched in Cape York and this is enriched in Mount Isa. The red bars represent NEMI minerals. And that's good news because we had a lot of NEMI minerals in Cape York and Mount Isa itself. Well, the other thing is for most companies, there are limited resources. You could do either Mount Isa or Cape York? So what we did is we compared the two and normalized it against one another and show what's more attractive in Cape York and what's more attractive in Mount Isa itself. And this is one of the plot. Basically, in Cape York, you look at a lot of things like associated with oxyphilic elements, tin, rare earth, tungsten, etc. And the one thing that really stands out is that Cape York, it's more endowed with heavy and medium rare earth compared to Mount Isa. Okay. The second thing is this: Cape York has been shown to have more lead potential than Mount Isa. You might not like it, but that's what the data is telling us. So whether there are lots of potential of lead in Cape York that's not yet discovered, I don't know. It's something that I think explorers should sort of try and go there and sort of find out. To summarize, this diagram sums up, what I've been talking about. Firstly, in Cape York, those elements in reds are ones that's preferential within Queensland that you go and explore for. And the ones in red on the Mount Isa sites are ones that's more potential in Mount Isa. The elements below that, germanium, yttrium, are ones that's higher. It's normalized to be ones that's potential in that region compared to the national average. Like I said, oxyphiles in Cape York, chalcophiles in Mount Isa. And and the maps in the Cape York ones has 68 elements that you could choose from, and we'll tell you where to look for as well. It's not an expensive project. It's only cost $400,000, and it has enormous benefit, which I think, explorers should take advantage of that. Even the National Geochemical Atlas, it's cost, but it still tells you where to look for, what to look for in Queensland itself. And finally, I have all the reports, all the links say that you could get access to that report and the database itself. Thank you very much.
Well, thanks for keeping us awake, Joe. That was awesome. Okay, does anybody have any questions? Yes, Johan has a question up the back.
Thanks for the talk. So as you go into the Cape York, you find very diverse geology. So you go probably from Proterozoic age rocks to Mesozoic age. Do you try to separate this prospectivity based on the underlying basement?
The problem with that is a lot of these sediments, like Cape York, a lot of the sediments are derived from the Cretaceous ones. So, we did try that. It didn't work very well at all. So we sort of decided to go back to just, the primary data itself. So no, the answer is that we tried, but we didn't, find it successful.